Welcome to this exciting video where we will dive into 30 fundamental questions on waves, the building block of understanding motion, force and energy and communication in science. Whether you are preparing for your exams or just curious about how waves work, this video will guide you through the essential from the definition of waves, medium through which waves travel, to the differences between mechanical waves and electromagnetic waves, and also transverse and longitudinal waves. We will break down key concepts like crests and troughs, compressions and rarefactions, and explore the important properties such as wavelength, period, wave speed, amplitude, and frequency. By the end of this video, you will not only master the basic but also gain the confidence to tackle wave-related questions in your physics and science exams. So grab your notebook, stay focused, and let's make waves simple and fun. The first question: what is a wave? A wave is defined as a disturbance or a vibration that travels through space or a medium, transferring energy from one point to another without the transport of matter. Matter in this case we mean solid, we have liquid, and we also have a gas. And in waves, solids, liquids, and gas through which a wave travels, we call it a medium. Therefore, a wave only transports energy, but it does not transport the particles of the medium through which it travels. Now, from this definition, we can come up with three conclusions. A wave only carries energy, that is the first one. The second one, a wave does not carry particles of matter. Then the third one is that a wave can travel in an empty space or in a medium, and we have said a medium is solids, liquids, and gases. Now we can demonstrate this by using this simple setup where we have a rope with alternate colors of green and red, and on these green particles, if we make a line like that and then we disturb this wave on this left hand side up and down, you will realize that the wave will move from the left side to the right side, and the position of the green particles will remain on the same line. Like in this case, if you disturb the particles at this end in an up and down manner, in this case the wave will move from left to right like this, but the position of these green particles will still remain on the lines that I made on the screen. Therefore, in this case, it means a wave can only move from one point to another, transferring energy, but the particles of the medium are not disturbed. The second question: state and explain two main categories of waves. The first category of waves is what we call mechanical waves, and we define mechanical waves as waves that require a medium to travel through. A medium in this case, it means matter, and since we have said a medium in waves represents matter, and matter is made up of three main states, first being solid, second being a liquid, and also the third being a gas. Then we will not be wrong by defining mechanical waves as waves which requires either solid, liquid, and gas to move energy from one point to another. So therefore, in this case, for mechanical waves, they can only travel if there is matter, that is solids, liquids, and gases. A good example is sound wave and also water wave. The second category of waves is what we call electromagnetic waves, and electromagnetic waves are defined as waves which do not require a material medium. So electromagnetic wave does not require solids, liquids, and gases, hence they can travel even in a vacuum, which is an empty space. A good example of electromagnetic waves is light waves. We also have X-rays, we have microwaves, we have radio waves which we use in phones and television, and many other examples. Therefore, it's very important for you to note here that for mechanical waves, they only travel when there is a medium, either solids, liquids, and gases, and if they encounter an empty space, they stop moving. But for electromagnetic waves, they move even without a medium. They can move in solids, they can move in liquids, they can move in gases, and also they can move in an empty space. The third question, what are two types of mechanical waves? Remember, we defined mechanical waves as waves that requires a material medium. In this case, we call the medium matter, that is solid, liquid, and gases, to move energy from one point to another. Therefore, we have two main types of waves that require solids, liquids, and gases for them to move energy from one point to another. And the first one is a transverse wave. A transverse wave, in this case, it has the highest point, which we are going to give a name shortly, and then it has the lowest point, which we are also going to name shortly. Another important feature of a transverse wave is that the particles are displaced in one axis while the energy moves in a different axis. So in this case, this is the movement of energy, and this is the movement of displacement of particles. So that's what we call a transverse wave. The second type of mechanical wave is a longitudinal wave, and a longitudinal wave has two main important features. The first one is where the particles are too close together, and in this case, it's a place of high pressure. This is what we call a place of high pressure. So we're going to give it a name shortly. Then we have a point where the particles are far from each other, and therefore the particles in this case have a lower pressure, and we're going to call it a rarefaction. So this is how a longitudinal wave looks like. Another important thing about longitudinal wave is that the direction of displacement of particles is the same horizontal axis with the direction of motion of energy. The fourth question, what is a transverse wave? A transverse wave is defined as a wave where particle displacement is perpendicular to the direction of wave propagation, or sometimes we call energy propagation. And we can show this using a very simple diagram here of a Cartesian plane with x and y axis. This is the y axis, while this one is the x axis. So in this case, where the two axes meet, we have a 90 degrees that is perpendicular. Therefore, for a transverse wave, it means if the particles are displaced in the y-axis like that, then the wave will move in the x-axis. So if you have a rope like this one you can see on the screen, if we decide to displace the particles or to kick this rope up and down, in this case we are displacing the particles. So in this case we are going to displace the particles up and down using this rod. Then the energy or the wave will move from left to right. So in this case, this is where the wave, or what we call the energy will be displaced. And we can see this, like you can see here. If I push this rope up and down, this energy is going to move from left to right. So when particles are displaced perpendicular to the direction in which the wave is traveling, that's what we call a transverse wave. The fifth question, what is a longitudinal wave? A longitudinal wave, we define it as a wave where particle displacement is parallel to the direction in which the wave is propagated or the energy is propagated. And we can demonstrate this one by having a particle here. This is the particle. If you push this particle in this horizontal axis to the right, this is the particle displacement. For a longitudinal wave, you will realize that the energy will also move in the same horizontal axis. This is the energy. So you can demonstrate this one by using a slinky spring, that like the one that we have here on the screen. If you have this hand and then you push this slinky spring to the right like that, you will realize that energy will also move in the same direction to the right. That is energy movement or a wave movement. So you can see this one here. I'm using this slinky spring to push these particles. The energy, you can see it here, it's moving to the right or in the same horizontal direction like that. So that's what we call a longitudinal wave. The sixth question, distinguish between a crest and a trough. A crest is defined as the highest point of a transverse wave, while a trough is defined as the lowest point of a transverse wave. So for you to have a crest and a trough, then you must first have a transverse wave. And in a transverse wave, we say the direction of displacement of the medium particles is 90 degrees to the direction of wave motion. Therefore, in this case, if we have the particles being displaced in this vertical axis, particle displacement here in the vertical axis, then in the horizontal axis we will have the wave propagation. Therefore, the highest point, this one here, is what we call a crest. This one is also a crest, and this one is a crest. And then the lowest point is what we call a trough. This one is a trough. This one is also a trough, and you can also call this one a trough. So a crest is the highest point of a transverse wave, while a trough is the lowest point of a transverse wave. The seventh question, define amplitude and state its SI unit. We define amplitude as the maximum displacement of points on a wave from the mean position, and this one shows the amount of energy that the wave has. Therefore, if the amplitude is long, the wave has high energy, and if the amplitude is short, the wave has less energy. So for you to identify the amplitude on this transverse wave, then you have to know that this vertical axis shows the displacement of particles from the mean position, while this horizontal axis shows the wave propagation. And another thing that you need to note is that we have a yellow line here, which we call the mean position, and we measure amplitude relative to this mean position, which is marked yellow here on the screen, like you can see. Therefore, in this case, if you need to find the amplitude, then you have to measure the distance from the mean position here to the maximum height through which the particles have been displaced, and this is what we call an amplitude. You can also measure it to the lower part here where the particles have been displaced on the lower side, and this is what we call also the amplitude A. So therefore, in this case, if you are told to measure the amplitude, you have to stand at this point here at the yellow part, then you measure the distance from that point to where the particles have been displaced here, and we call this one amplitude. Or you can stand on this upper side from this yellow mark or line to the maximum displacement of particles. This is what we call an amplitude. So you can do it at any point where you have a crest or a trough. This is an amplitude, and also here you can get an amplitude. So the SI unit of amplitude is meter. So we measure amplitude in terms of meter. Sometimes you can get it in centimeter and millimeters. Question 8. Define wavelength of a wave and state its SI unit. We define wavelength of a wave as the distance between successive crests or successive troughs. When we talk about successive, it means crests should be following each other. If it is troughs, the troughs should be following each other. Therefore, in this case, if you have a wave train like this one, with this vertical axis showing displacement of particles, while the horizontal axis showing distance covered by the wave. Therefore, in this case, you have to look at the first crest. This is the crest. Then you look at the immediate crest, which is coming after the first crest. This one here is another crest. So the distance between this crest and this crest, this one here, is what we call the wave length. Or if you use the troughs, then you have to look at the first trough. This is the trough, and then this is the successive trough, the one which is following the first one. Therefore, the distance between these two troughs from here to this point here, this is what we call the wavelength. So you can get the wavelength either by using crests or using two successive troughs. Sometimes we define wavelength as the distance between two particles which are in phase. Particles are in phase if they are moving in the same direction and they are at the same maximum displacement. And I want to give you a good example. Look at this particle here which I've marked. This is particle 1. This particle, since the wave is moving from left to right, this particle at this point is moving up like that. Then the second particle, which is at the same level and moving in the same direction, is this particle here. Let's call it 2. This particle is also moving up like that, and the height of these two particles is the same. So we can also get the wavelength of the wave by taking the distance from this particle 1 to this particle 2. Particles which are in phase, moving in the same direction and also having the same maximum displacement. Now the SI unit of wavelength is meter. Sometimes you can get it indicated in books in centimeters and millimeters, which are the subunits of meter. Question 9. What is periodic time of a wave? Periodic time, sometimes we call it just period, and it's defined as the time it takes for one complete wave to pass through a given point. And for you to identify periodic time, then you must have a wave train like this, with this vertical axis showing displacement, this displacement of particles, and then this horizontal axis this time showing the time taken for a wave to move. So therefore, in this case, for you to identify periodic time, then you must get two particles which are in phase. And I said particles which are in phase must have same maximum displacement and should be moving in the same direction. This one now looks familiar. Therefore, for you to get a particle in phase, then you must look at, you can take a point at the top of a crest, like this one is a crest. You take this point here, or this particle here. Then the second particle which is in phase is in the next crest. This is the next crest. So if you take a particle here and another particle here, and then you get the time that it takes for a wave to cover this or to move from this particle to this particle, this is what we call a period. Then for another particle which is in phase, you can look at this trough down here. This is a trough, this is another trough. Then if you take a particle at the maximum point of this trough and another particle on this successive trough, then you get the time it takes for this wave to pass or to move from this first point to this second trough. This is what we call a period. Now you need to distinguish between periodic time and wavelength. For wavelength, we had a graph or a wave train of displacement against distance. But in periodic time, we have a wave train of displacement against time. So if you have at the horizontal axis here, you have it as time, then the time from crest to crest or trough to trough is what we call a period. But if you have distance down here, then the distance from crest to crest or trough to trough will be wavelength. So that's the main difference. Question 10. Define frequency and state its SI unit. We define frequency as the number of waves. Sometimes these waves we call them oscillations. Number of oscillations that passes a fixed point in unit time. Unit time, sometimes we call it per second. Per second. So you have to find the number of oscillations or waves that passes through a fixed point in 1 second. Therefore, for you to illustrate this one better, then you should have a wave train like this one, where we have this vertical axis showing displacement of particles, while this horizontal axis showing time taken by a wave to move through this fixed point. So you want to take a case where from the beginning of this wave here, call it A, to the last part of this wave here, call it B. It's taking only 1 second for this wave to move. So from that point to this point is 1 second. Then now for us to get frequency, then we have to count the number of waves which this wave has covered in 1 second. From point A to B, how many complete waves or how many complete oscillations are there? And how do you count an oscillation? You count an oscillation by looking at two particles which are in phase. Like in this case, the first particle in phase is called this one 1. This second particle which is in phase with particle 1 is this which we have called 2. So in this case, from this crest to this crest, this is the first wave. Then the second wave is from particle 2. Another particle which is in phase with particle 2 is this particle 3. Therefore, this is the second oscillation or wave. Then another wave that we have here is from particle 3. Another particle which is in phase with particle 3 is this particle 4. Therefore, another wave that we have here is between 3 and 4. So this one is wave 3. So in this case, we have 1, 2, and 3 waves covered in 1 second. Therefore, in this case, the frequency of this wave is 3 waves per second, which sometimes we call 3 Hz. Remember, 1 Hz is the same as 1 per second. Very important for you to know that. Then the SI unit of frequency is Hz, whose symbol is capital H, small z. And we have said 1 Hz is the same as 1 per second. Question 11. What is wave speed? Wave speed is defined as the speed at which a wave travels through a medium. So in this case, if you have this wave train with this axis and this axis showing displacement, this displacement of particles in the medium, while this one shows the distance covered by a wave. Therefore, in this case, for you to get the wave speed, we can get it in two ways. First, we get it from a formula that we know from mathematics. Speed is equals to distance covered divided by time. But now in this case, we're going to use a distance covered by two particles which are in phase. So in this case, the particle in phase is here, this crest to this crest. And if you get the distance between two successive crests, we call it a wavelength, and we give it a simple lambda, this one here. Then we divide by the time covered for the same distance. So at a time covered from crest to crest, we call it periodic time. So if we also get the time from this point to this point, we call it periodic time, and we give it capital T, that is periodic time. Therefore, in this case, wave speed can be obtained by wavelength divided by period, that is periodic time. Wavelength is given by lambda, while periodic time is given by capital T. But also remember, we have said periodic time T is a reciprocal of frequency. So if you know the frequency, therefore you can get speed, the speed of a wave, as the wavelength lambda, then times 1 over periodic time. 1 over periodic time is f, therefore speed of a wave can be obtained by lambda times frequency. And that's what we call the wave equation, where we give v as the wave speed is equals to lambda frequency. That is the wave equation. Question 12. What is constructive interference? Constructive interference is defined as when two waves meet in phase and their amplitudes are together. So in this case, you can have two separate waves. This is the first one with an amplitude of, let's say, 1 centimeter. Then you have another wave like this. Then the amplitude of this one is also 1 centimeter, the maximum displacement. Now when these two waves meet and they are in phase, now they will form a single wave, but now in this case the amplitude will double up. The amplitude will double up so that now it forms an amplitude of 2 centimeter. Remember, we said that an amplitude shows the energy that the wave has. If two waves which are in phase meet, they will form a wave with higher energy than the individual waves that met. Now we can demonstrate this one by using two sources of waves. This is the first source and this is the second source. Now when these two sources emit when they emit the wave, they will produce waves which will interact, and the wavelengths will merge. And now when the wavelengths merge, what you see as bright green, in this case, this is what we call constructive interference. This constructive interference, it means these two waves, one from down here, second one from up here, when they meet, the crests will meet with crests and their amplitude will double up. It will form this bright part, and the trough will meet with another trough. They will double up. They will form another bright patch on this case. What you see as dark spots, that's what we call destructive interference. Question 13, define destructive interference. Destructive interference is when two waves meet out of phase and their amplitudes cancel each other out. So in this case, if you have the first wave here, where you have the wave like that with an amplitude, say, of 1 centimeter, and then you have another wave down here, but now they are meeting out of phase. In this case, you have, instead of the trough moving up first, we start with a crest, then a trough, a crest, a trough, and then finally a crest. Therefore, in this case, also the amplitude is 1 centimeter. Now, when these two waves meet, they will form a wave where this crest will cancel with this trough, and in that case, the energy will cancel out. Therefore, there will be no trough, there will be no crest. Therefore, in this case, we will have a wave which looks like the diagram 3 that we have here with a 0 amplitude. Therefore, in this case, we can demonstrate this one also by using two sources. This is the first source of the wave. This is the second source. Now, if you have source 1 and source 2 producing a wave, these two waves will meet out of phase, and when they meet out of phase, the energy will cancel out and they will form these dark spots that you can see here on the screen. Now, this dark spot is what we call destructive interference. Question 14, what is required for mechanical wave to travel? So for mechanical wave to travel, remember we defined the mechanical wave as waves which require solid, liquid, and gas for them to travel from one point to another, and therefore we said it can never travel in a vacuum. Therefore, in this case, solid, liquids, and gases, we call them a medium. So in the first option here, electricity, no. Magnetism, no. A vacuum, no. Mechanical waves cannot travel without particles. Therefore, the correct option here is D, which is a medium. And in a medium, we said we should have solid, we should have liquid, and then we should have a gas medium. Question 15. What type of wave moves the medium perpendicular to the direction of the wave? So before we look at the options given, let's look at the wave that we have here on the screen. In this case, we are moving the medium particles up and down. This is the medium particles, while the wave is moving, or the energy is moving in this horizontal direction. Therefore, in this case, if we draw a very small Cartesian plane here, the wave is moving in this direction while the particles are moving in this y-axis. Therefore, in this case, this angle here is 90, which is perpendicular. And what type of wave do we have here on the screen? A, longitudinal wave, wrong. Seismic wave, wrong. Surface wave, wrong. Transverse wave, this is correct. It's a transverse wave whose medium particles move perpendicular to the direction in which the energy or the wave is moving. Question 16. What are the highest part of a transverse wave called? Now, before we look at what they are called or the options given, I want us to look at a good example of a transverse wave that we have here. So in this case, when this transverse wave is moving, it's forming highest point, and also it's forming the lowest point. Like in this case, the highest point of this transverse wave is here, and we call it a crest. And then the lowest point of this wave down here, we call it a trough. Therefore, in this case, the highest point of a transverse wave, a crest, this is correct. So it's a crest. Compression, no. Rarefaction, no. Trough, no. Trough is the lowest point. This lowest point here is what we call a trough. Question 17. In a longitudinal wave, what are the areas where the particles of the medium are spread apart called? So in this case, if you have a longitudinal wave here, we have an area where particles are so close to each other, and we call it a compression. That's an area of high pressure. Then we have an area where particles are far away from each other. This one we call it a rarefaction, an area of low pressure in a longitudinal wave. So the question is, what are these areas where particles of the medium are spread apart called? So in this place where particles are spread apart, we call them rarefaction, and the correct answer is A. Crest, this is the highest point for a transverse wave, so it's not an area where particles are spread. Compression, this is a place of high pressure where particles are so close to each other in a longitudinal wave. So D, trough, this one is for a transverse wave, the lowest point of a transverse wave. Therefore, the correct one for particles spread in a longitudinal wave is called a rarefaction. 18. What is the SI unit of frequency? A, watt. Watt is for power. Second is for time. Hertz is for frequency. Meter is for length. So therefore, the SI unit of frequency is C, which is Hertz. Question 19. What happens during a refraction of a wave? Remember, we define a refraction as the change in direction of a wave at an interface when it's moving from one medium to another. So in this case, let's look at the options given. A, they bend as they enter into a different medium. This is correct. B, they disappear. No. C, they split into two. No. D, they bounce back from the surface. This one is reflection, not refraction. So the correct answer here is A, they bend or they change direction as they enter a different medium at the interface. Question 20. Regular disturbances that carry energy through matter or space is A, a trough. No, a trough is the lowest point of a transverse wave. B, a wave. Right, a wave is a disturbance that carry energy through matter or space. C, energy. No, energy is the ability to do work. Then D, crest. No, crest is the highest point of a transverse wave. So the correct answer here is B, a wave, which is a disturbance that carry energy through space or matter. 21. Electromagnetic waves include the following except. So in this case, we have been given 4 options. 3 are electromagnetic waves while 1 is not. But before we look at the options given, in this case, let's remember that electromagnetic waves, these are waves which does not require any material medium for transmission. Hence, they can travel or they can transmit energy in a vacuum. And a good example of them is radio wave. We have microwave. We have infrared, we have visible light or human sight, then we have ultraviolet, we have X-rays and gamma rays. So now let's look at the options given if they appear among the 7 electromagnetic waves that we have just mentioned. A, doing the wave at the football game, it does not appear among the 7 that we have listed. X-rays, they are there. Radio waves, correct. Microwaves, correct. So the one which is not electromagnetic wave is A, which is doing the wave at the football game. Question 22. Which wave in the diagram has the greatest wavelength? Remember, wavelength we said is the distance between 2 successive crests or 2 successive troughs, or sometimes we defined it as the distance between 2 particles which are in phase. And in this case, we want to look at the crest to crest distance. I want to begin with the first one. The first one, we have crest to crest distance is this one, call it lambda. Then the second one, crest to crest distance, is this one here, lambda 2, this one. Then the third one, crest to crest distance, is this one here, lambda 3. Then the fourth one, crest to crest distance, is this one, call it lambda 4. So in this case, which one has the greatest distance from crest to crest? In this case, you will see this number 3, the wave 3, has the greatest distance from crest to crest. Therefore, in this case, our correct answer is C, where C is a wave with the greatest wavelength. Question 23. Which letters represent the crest of a wave? Before we look at the options given, remember a crest is the highest. We defined it as the highest point in a transverse wave. Therefore, in this case, let's label the parts of this wave. In this case here, we have a crest. This is also a crest. Then this down here is a trough, the lowest point of a wave. Then this line in between here, we have A, C, E, and G. This is what we call a mean position. Now, in this case, we have two crests. This is the first one, that is B. And then we have, this is the second one, that is F. So therefore, A is the crest. No, it's at the mean position. B and F are the crests. That is correct. C, F is the crest. We also have B, so this one is not correct. Then D, B, and D. B is the crest while D is a trough, so this one is wrong. So the correct answer here, the one which represents a crest, which is the highest point of a wave, is B and F. Question 24. Which letters represent the trough of a wave? Remember, we defined a trough as the lowest point in a transverse wave. Therefore, in this case, let's label the parts of this transverse wave. These are crest. F is also a crest, and they are the highest point of the wave. A, C, and G, this is a mean position of the mean point. Then now D is the trough, and this is the lowest part of the wave. Therefore, let's look at option A, C, and G. No, they are the mean position. Then we have D. This one is correct. This is the trough, so the correct answer is B. Then C, A. No, this one is at the mean position. Then D, B, and D. B is the crest. Then D is a trough. Therefore, in this case, this one does not represent the trough. So the correct answer is D, which is a trough and the lowest point of a transverse wave. Question 25. A mechanical wave cannot travel through. A mechanical wave, remember, we defined it as a wave which requires a material medium. And medium, in this case, we said it's matter. And matter, in this case, it's solid. We have liquid. And then we have a gas. Therefore, mechanical waves can only travel in solids, liquids, and gases. Now, in this case, they are asking a mechanical wave cannot travel through. In this case, A vacuum, B, air is a gas, therefore it can travel through a gas. C, water is a liquid, it can travel through a liquid. And then D, glass is a solid, and the mechanical waves can travel through solid, liquids, and gas. So the place where a mechanical wave cannot travel is in a vacuum or an empty space, because there is no matter or there's no medium there. So the correct answer here is A. Question 26. When the frequency of a wave is increased, what happens to its wavelength? Remember, we defined frequency as the number of waves per unit time, while we defined wavelength as the distance between two successive crests or troughs. So in this case, before we look at the options given, I want us to look at the wave that we have here. And in this case, I want to introduce a frequency of 2 Hz, and then now I want you to look at the wavelength which is formed. And in this case, you will realize that the wavelength ranges from 1 to 5 here. Therefore, in this case, 5 minus 1 is 4 centimeter. while when I introduce a frequency of 4 Hz, I want you to note the wavelength of this wave, and in this case now it's ranging from 1 to 3. Therefore, in this case, it means 3 minus 1 is 2 centimeter. Therefore, in this case, when you increase the frequency of a wave, the wavelength decreases, while when you decrease the frequency, the wavelength increases. Now, in this case, we are told if you increase the frequency, like you increase from 2 to 4, what happens to its wavelength? And you can see here it was 4, the wavelength has reduced to 2. Therefore, when you increase the frequency, the wavelength decreases. Now let's look at the options that we have been given. A, the wavelength increases. This one is wrong. B, more specific information is needed to form a conclusion about the wavelength. No. Then C, when you increase the frequency, the wavelength decreases. This one is correct. While D, the wavelength is not directly affected by the frequency of a wave. This one is wrong. So the correct answer here is C, where when you increase the frequency, like in this case from 2 to 4, the wavelength decreases from 4 to 2 in our case on the screen. Question 27. The types of waves that require a medium to pass are A, mechanical waves, B, electromagnetic waves. Now, mechanical waves, we define them as waves which require matter, that is solids, liquids, and gases to propagate. So in this case, this one requires a medium. Electromagnetic waves, these are waves which does not require any material medium to travel. They can even travel in a vacuum. So in this case, no matter required. Therefore, in this case, the waves which require material medium to travel are mechanical waves. The correct answer is A. Question 28. What property of this wave is represented by letters B and A? So in this case, if we have this vertical axis representing displacement, this displacement of particles from the mean position, and the horizontal axis representing distance covered by the wave, therefore B will represent amplitude, is amplitude. Then A will represent the distance between two successive troughs, which we call the wavelength. The wavelength. Therefore, in this case, B represent amplitude, A represent wavelength. Therefore, the correct answer, let's look at A, crest and trough, no. Amplitude and wavelength, this is correct. Wavelength and trough, no. Trough and period, no. So in this case, the correct answer is B, amplitude and wavelength. Question 29. Which of the following can sound travel through? A, solid, B, gas, C, liquid, D, or the above. Sound is an example of a mechanical wave, and it can travel through both solid, liquid, and gases. Therefore, the correct answer here is D, or the above. Then question 30. Which material does sound travel fastest? Sound requires a material medium to travel, and the more the particles are, then it means sound will travel fastest. And if you compare the number of particles in gases, solid, and liquids, you will realize that solids have more particles, and since sound requires more particles to travel, therefore sound will travel fastest in solid. Then liquids have more particles than gases, therefore it will travel relatively fast in liquids, and then it will travel least in gases because the particles of gases are very small.